Okay, so today is 5.1. Maybe going into 5.2 a little bit because I looked further and 5.3 might take longer than these two sections actually. So we'll just see what kind of happens. Maybe we'll do the first 4 pages and then the fifth and start 5.3 next time we meet. We'll just see. But again, we're doing this instead of meeting in class because my poor little baby son has a fever, so I need to stay home with him. But I think you're gonna like this. We're going back to first derivative stuff, logs, exponent, trig functions will still be in here, but mainly going back to just our favorite of power rule. So also this chair that I'm in is very squeaky, so please forgive me. But example 1. Oh yeah, so objectives. Use the first derivative to find critical values in local extrema. We'll talk later about what the heck those terms mean. But basically, a critical value is a potential location of a local extrema. In a local extrema is a max or a min. Okay. So example 1, let f of x equal x cubed minus 3x. Where does f have a horizontal tangent line? So horizontal tangent line, that's here and here. That's where we have the slope of 0. Why you had these questions on test 1, right? Always leading you into the next thing. So x equaling -1 and x equaling 1, we have these horizontal tangent lines. So there exists local extrema at these points. At these points. Perfect. There we go. So extrema being like a max or a min, a hill or a valley. So now to go deeper, consider f prime of x. The derivative of f gives us the behavior of the graph of f at each point, right? So the one I'm going to call it under, right, tells us the behavior of the graph at each point. So by behavior, we mean increasing, decreasing, was it constant, and then back to increasing or decreasing again. But by behavior, we mean increasing or decreasing, constant. So if f prime is positive, if the derivative is positive at some point, then the graph is increasing. Increasing. Because notice here, all of these tangent lines, they have a positive slope, right? So if I have like these million infinite tangent lines off of those points, they have positive slope. So then notice if I'm between -1 and 1, these tangent lines have negative slope. So a negative slope tells us where the graph is decreasing at that point or between those points. So if f prime is 0, right? So if we have horizontal asymptotes, aka meaning, let me get a good color. Not good, right? Meaning the slope of the tangent line is 0, then the graph has a local extrema at that point. Okay, so this is another reason why derivatives are important. It tells us the behavior of the function itself. Where are we increasing, where are we decreasing, where do we have a hill, valley, max, min. So example 2, basically for this graph, we're going to act as if we don't have this picture and we're going to try to figure all that out. Oh, wow. Did y'all see that, Nat? Oh, I get it. Oh, sorry. That's going to be obnoxious. But example 2. So same function. We're going to find the derivative. Then we're going to create this thing called a sign chart. If you just came from college algebra, this should be old information. If not, we're going to go into detail about it now. So you're still in good hands. So where is f prime increasing? Where is f prime 0? And where is f prime less than negative? Excuse me, I can't talk, less than 0 or negative. And then we're going to state where f is increasing and decreasing. Okay, so what that means is that step one, we're going to find f prime of x. Step two, we're going to set the derivative equal, to 0. And then 3, we're going to solve for x. So basically that is our mathematical 3-step process, broad strokes of what we're actually doing, like pen to paper type thing. So we know that f prime of x is equal to 3x squared minus 3. We're going to set this thing to 0, 3x squared minus 3. Now we're just going to solve. So they both have a 3, so we're going to factor out a 3. And then this is a difference of squares, so it factors into x plus 1, x minus 1. So then we see, that x equals -1 and +1, right? Because you set this equal to 0 and solve. Set this equal to 0 and solve. The 3 doesn't have an x. So if we set it equal to 0, it doesn't make any sense, right? It's not a solution. Okay, so here, these 2 points are what we call critical values. Critical values. They are potential locations of local, that's an L, it's the first of L, local extrema. Okay, so here's the sign chart business. Called a sign chart, not a number chart. Okay, sign chart, not a number chart. So here is our x-axis. We're gonna have some x, f prime of x, and then plain old f. We're gonna put 2 numbers down in here. Our x's of interest, that's -1 and 1. So we're gonna choose random numbers to the left of 1, between -1 and 1, and less than -1 to help us fill in our sign chart. Okay, by sign chart, we mean plus signs and minus signs, positive or negative. That's what is meant by a sign chart. So we're going to choose test values. You can choose any number you want, as long as they're not -1 and 1. It is a number line, so your numbers do have to be in a numerical order. That's very important. Number line, they have to be numerical order. Otherwise, things go haywire. So my favorite numbers when applicable are 10, 0, and -10. You 1000% do not have to use these numbers, but I just like them because they're easy to work with. Like 10, not too big, not too small. Easy to add and subtract, multiply, divide by 10. And then 0, hopefully, also just super easy and nice to work with. So what we're going to do is we're going to take these test values and we're going to work our way up the ladder. So we are going to pop -10 in to the derivative. Okay, also, this is known as the first derivative test. It's called the first derivative test. So mathematicians prior to inventing the math, they called it like they saw it, right? So things are called by what they do say are or mean. So I'm going to pop -10 into my first derivative because, again, this is called a first derivative test, right? All right, so if I pop -10 in to say here, then we have negative times a negative, which gives us a positive. Okay, again, I do not care what the actual number is, don't care. What I do care about is that this is positive. So what this means to us, remember, is if it's positive, f of x is increasing. Now, if I choose 0, that's a positive times a positive times a negative, which spits out an overall negative. Again, don't care what the number is. I just care that it's negative. So from here, the second bullet, if the derivative is negative, f is decreasing. Same thing if I pop in 10, that's 11 times 9. Again, a positive times a positive. I don't care what the actual number is. I just care that it's positive because that tells me that f of x, or the function, is then increasing at that point. So I now know, I can say with certainty, because we change direction, right? From left to right, we go up, then down, that this is a max, right? We kind of create that hill. And then at 1, we're down, then up. We have a min, again, because we've created that kind of like valley. So f is, use my shorthand, up arrow increasing from negative infinity to -1, and then union 1 to infinity. Notice we are using parentheses because we cannot be increasing and decreasing at the same point. So parentheses around there. And then decreasing from -1 to 1. Again, note the parentheses because we are not both increasing and decreasing at a certain point. Okay, so that's page 2. The next, this is page 1. The next page will have, excuse me, the next video will have page 2.